The next section is a little bit different than the first, but at some point they will kind of overlap each other in section 8.3. But this is kind of a completely different thing that we're going to be talking about. It's called inverses of relation. So how do you find the inverse of relation, and how do you determine whether the inverse would be a function? So the definition of inverse of relation. So if you remember, a relation is just like any set of ordered pairs. So a relation is obtained by switching the coordinates of each ordered pair. So if you have a bunch of ordered pairs and you switch the coordinates, you now have that relation's inverse. The very simple example, we're just going to take a bunch of coordinates, as you can see here. We're going to find the inverse of f. So this is considered f, all these points. We're going to find the inverse of f. We'll call that function g, and then we'll graph both relations. So let's do g, and we're just going to switch all these points. So instead of having x, y, right, we're going to be switching around to say like y, x. So our new values for each one of these, put a little bracket here, would be 2, -3, 4, -1, 3, 0, 8, 2, 7, 5, and 8, 7. All right, so in this color, I'm going to graph all these points, put them on our table here, or our coordinate plane. So we have 2, -3, put a dot there. 4, -1, which is here. 3, 0. 8, 2, should be here. 7, 5, all the way up here. Yep, 8, 7. Okay, so I got them all. 1, 2, 3, 4, 5, 6. All right, and then we're going to change the color, and I'll make this one red. So we'll do red is the f function. So we have -3, 2. -1, 4. 0, 3. 2, 8. 5, 7. There we go. 7, 8. As long as I did this correctly, hopefully you can tell what's going on whenever you switch the ordered pairs. There's actually a symmetric line that's going through here, and if you could draw it to where you'd split the entire graph in half so it would match a line of symmetry, it would actually be right through this diagonal. If you look at this going diagonally, right, we can look at this and say if we go straight diagonal, which I'm not going to be able to do a good job at cutting this in half, but if you were to cut this directly in half as a diagonal going through like the top rights of these boxes here, and you could continue doing down here, it should look the same on both sides. This is how all inverse functions operate. So there's a symmetry line across, specifically this line is called y equals x. So if you were to draw this black line across, this is the line y equals x. That just means when you plug in like 1, you get 1. 2 is 2. 3 is 3. So right, so the y and x are the same. So if you draw this line every time, you can tell what's in inverse of each other, right? So these dots kind of match up on both sides. It also helps us find out whether or not we graphed everything correctly. And that's what an inverse is, right? You're just switching the order of pairs. And it creates a different type of graph, specifically symmetric to this line, y equals x. Okay, so let's try something a little different. Now we're actually going to graph something, not just points. So consider the function with the domain as a set of all real numbers, and the equation is y equals x squared. We know what this looks like, so we're going to graph this then. What is an equation for the inverse of this function? The way you do that is actually really simple, because we can't just switch the x and y's like for the numbers in the order of pairs. You could do that, but there's a lot of order pairs. But instead, we're just going to actually switch the x and y in the equation, and then we're going to solve for y. So it's a very simple process. Instead of writing y equals x squared, we're going to write this as x equals y squared. So I just literally switched the x and the y around. Then we solve the equation for our new y. So how do you get rid of something that has a squared? Well, you could do a couple things. We could do our new thing where you do a square root on both sides. I mean, that's the old thing. Or the new thing where you do the 1/2 power, right, to get rid of it. But remember when you do this, that we would get two different things. You get plus and minus the square root of x equals y. So we kind of talked about this before, like where it only gives you like the positive version. It's not the negative version. We're then going to graph this and the inverse on the same coordinate axes. So I would probably just pull up Desmos. See if I can do that. Easiest way to do it. And then we're just going to type this in here. Y equals x squared, which you already know what it looks like. We have this. And then we'll put in the square roots of x here. So we have y equals square root of x. Not sure how to enter square root. Nope. Let's try this. Here it is. Square root of x. So remember, that gives you like that sideways curve here. And we would also need the negative version of this. Y equals negative square root of x. To get both of them. So if we include both of these, we get the inverse. Where if you draw a line straight through this diagonal, it would be the same on both sides. So let me show you that too. Y equals x. There's the purple line, as you can see. If you could see this, right, going through, if you cut it right there, it looks the same on both sides. This is like coming down out here, which follows this. These are the same on both sides, the red and the blue here, and the same thing coming out. That would make them inverses. Okay. So graph the function inverse on the same coordinate axes. Is the inverse a function? We got to include both, right? So yes, if we include both. We have to include the positive and the negative. Man, this is not working out for me. Equations. So for instance, it would look something like this. I'm just going to make a sketch of it. It's not going to be perfect. It'll be something like this, right? And then the other one, we'll do in blue. Looks something like this. Oh boy, that's terrible. And then this way as well. You get the idea. So here's the line that you would draw going diagonally. That would be the same on both sides. If you were to fold it on that. Might be hard to visualize, but that's what's going on there. Okay, the domain and range for this. Well, we should already know the domain and range for the original problem. The domain for y equals x squared, which is my red one, if you remember, it extends in both directions. It goes this way and it goes this way forever. So the domain is all real numbers. So we can use the R symbol. Or you could do negative infinity to positive infinity. The range is your y values. So it starts at 0 and goes up to infinity. So we'll just say from 0, including it, up to infinity. Now, what's the domain and range of the inverse? Now, remember, the inverse is this. Y equals plus minus the square root of x. That's my blue one. Let's talk about the domain. That's the x values. Ooh. So the x values, if you look across the x-axis, it does not go into the negatives at all. So it starts at 0 and goes up forever, to infinity. So we'd say from 0 to infinity. Could you guess and see what the range would be? This is the y values we're looking at. If this extends forever this way, going up and up and up, slowly, but eventually, and this extends this way, going lower, 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 right? It covers all of the y values, so we would say that is all real numbers. Hopefully you can see what's going on here. When you have the original, and you know the domain and range, you kind of already know the inverse's domain and range. What's happening? Just like we did before, we switched the x and y's, the domain and range also switches. Same thing happens. All right. So one way you can test to see without drawing the inverse function to see if you get a function is a horizontal line test. So if you remember back here, this picture here, the blue one, is not a function, because if you did the vertical line test on this one, it would fail, right? You draw a vertical line and boom, it hits twice. Anywhere pretty much over here, you'd hit twice. So if you want to test to see if the inverse is a function, you do the horizontal line test. This is used on the original function to see if its inverse is also going to be a function. So you don't have to draw one necessarily. We're just going to do the horizontal line test. So we're going to go across left to right now. So you have two functions graphed. Tell where the inverses of the graph functions are functions. Okay, so this original one, right, you would use a vertical line test on it, and this is a function, right? So the question is the inverse a function as well? So we're going to use something called the horizontal line test. So we go across this way. And if you ever hit more than one time when you draw horizontal lines, then you know that the inverse would not be a function. So this is hitting so many times it's ridiculous. So we would say, no, this fails. If you remember before, we called this vertical line test VLT. Now it's going to be called HLT, horizontal line test. The second graph, which is down here, if we go across to talk about its inverse, this also hits more than once in many places that you draw across. It hits twice. That would also fail. So no, this also fails HLT. So if you drew the inverses of either one of these, it's not going to be a function. Now, domain and range. Let's erase all this. All we have to figure out is the domain and range of the original, because then we'll know the inverse. All right? So we have domain and range for the original function, and then also the inverse. So let's fill in the first domain and range of this one over here. The domain is the x values, and it clearly looks like it's going to continue going in the same kind of pattern, right? Forever going this direction, and forever going this direction. So we would say the domain is across all the x values, so I would say it's all real numbers. The range is the y values. It has a maximum point and a minimum point. We just have to figure out what that is. So it goes up to 3, it looks like. That's the highest point. These are like waves, right? It goes up to the 3, and the lowest point would be down to -3. So the way we write that, since it touches those points, the highest is 3, the lowest is -3. We would say from -3 up through 3. And then the reverse of this would be the domain and range of the inverse. So if we just reverse these answers, -3 to 3 is the domain, and the range would be all real numbers. Now do the same thing with the other function, domain and range. The domain here is from left to right. Oh, this is also extending forever in both directions. So it looks like it will cover all the negative x's and the positive x's because it keeps going forever. So we're going to call this all real numbers as well. However, the y-axis for the range, this has a maximum point here at 2. But since it goes down forever, it will never have a minimum point on the y-axis. So we can say this goes from -infinity, right? We have to go from low to high. So it goes down forever. So we go -infinity up to and including 2. So that would be a bracket. Then the inverse, pretty simple. Flip it around, which would be -infinity to 2. And the range would now become all real numbers. So So it's pretty easy to get the inverse without having to have the picture. The hard part, I think, is still getting domain and range off the original graph. But just switching these around is not too bad. Oh, there's our team huddle. So I'm just going to go through some of these problems. I don't think there's anything left besides team huddle to help you out with some of these. One, I don't think is an issue. We did one just like that. 2, determine if the inverse of the graph function would also be a function. Okay, how do you do that? How? HLT. Determine if the inverse is also a function. So this is a function, right? It passes the VLT. The question is, does it pass the HLT? So if you go across, you can do it as many times as you want. This is only ever going to hit one time. So we'd say, yes, function. Inverse is a function. Inverse is a function. I'm getting there. Y passes HLT. Horizontal line test. Then you just do the same thing for these ones. So this original one is a function. It passes the vertical line test. Unfortunately, if you go across, specifically like up here, or even down here, it doesn't really matter where you go, you're hitting more than one time. So this is not. Nope. Not a function. This fails. HLT. And the last one, well, it's a horizontal line itself. So this is a function, but the inverse would not be a function because if you specifically went across this line with your HLT, you're hitting every single point. So this is no. This fails. HLT. And I believe the inverse of this would be like this. A vertical line going this way, right? Because if you draw the diagonal here, it's going to match up. We're going to practice actually drawing some of these before we get to the last section, because I want to cover most of this stuff before we end this. We're going to sketch a graph of the inverse, and I don't want you to just guess what it looks like, even though you should know what the inverse of this already looks like. But what you could do is you could like take some of the points and reverse the order. There would be like this, 1, 1. That's a really easy reverse, right? 1, 1 is still the same thing as 1, 1. Here you have -1, -1. Pretty easy switch, so that means it's also in the inverse. How about something like this harder one up here? This would be 1, maybe 1.5-ish, comma 4. So 1.5, whoops, 0.5, comma 4. All right. And then the other inverse would be 4, 1.5. So 1, 2, 3, 4, and then 1.5 like that. You can do the same thing on this one down here. Flip that around. It'd be -4, 1. I'm sorry. This would be -1.5, comma -4. Then you flip that around. It'd be -1.5, or -4, -1.5 like this. So it'd be going like that. And that's our inverse. Not a great sketch, but you get hopefully get the idea. All right, the last graph we have here, I don't know if you noticed this, but this is basically, this line right here is the y equals x line. So all these points that would get switched are all the same. You have 0, 0. You have -1, -1. Like these always would be the same thing. So if we're trying to draw the inverse, this is all the same up until 2, 2. So, and you can draw all of those points and put the dots on there. Like so. So now this line doesn't change at all because all these points are the same. If you switch the x and y, it doesn't make a difference. Now let's do some other points that might, change things. So if we go up to here, this is 5, 2. Whoops, 5, 2. So the inverse would have to be 2, 5. That's what we need over here. 2, 5, like that. And you could do the points in between, but we know it's a straight line. So we just need to connect them. Like so. And let's do another one here. We have 7, 0, which means we have to have 0, 7 over here. So 0, 7 would be this. So these also connect. And since we're going in the same direction here, you could do other points here, but it's going to keep going off in that direction this way. So that would be the inverse. If you drew it over here, it would look something like this. Up to what, 7? Oh, this one goes to 5. It goes up to 5, and then it go up this way, and then across that way. That would be the inverse. All you have to do is just pick some points and just reverse the order. Last thing that we're going to go over, finish this up, is solving other equations to find the inverse. So what do you do every single time? You just switch the x and the y, solve for y. So we're going to switch this, make this x equals 3y, solve it for y. So just divide both sides by 3. So x over 3 equals y. And that's your equation. You could rewrite it with y first. So these two are inverses of each other. And if you graph them both in the calculator, you would see how they're inverses. How about b? You'd switch the x and the y, so we get x equals 5y plus 10. Solve them for y, minus 10 on both sides. X minus 10 equals 5y. Divide both sides by 5. So this here, x minus 10 over 5, would equal y. You could go a little bit further with this. If you divide them both by 5, you can make x over 5 minus 10 divided by 5 is 2. So this would be the same thing as this, as an inverse. These are inverses, right? These are inverses. Can I turn this sideways? No, doesn't make a difference. Okay. This is working out great. Okay, and the last one I think I'll do, switch the x and y, so you get x equals y minus 7 over 3. Trying to get y by itself, you would multiply both sides by 3. So you get 3 times x equals, this goes away, y minus 7. Add 7 to both sides. So 3x plus 7 equals y, which you could write this way. So then these two are inverses of each other. So there's a couple left for you to try. I think there's like 3. There's those 3. That's all for the huddle. And to go back and do number 1. And that should finish up the notes for today. And then tomorrow on 8.3, we will cover how these two things interact. The composition of functions, which is 8.1, and inverses, which is today, 8.2.